Okay, so we need to find the acute angle between line 1 and the z-axis, alright, where n is the foot of the perpendicular from the origin. The ON is -8. Okay, so from here, first one we need to find the acute angle between line 1 and the z-axis. Likely is that we're actually finding the angle between two lines, right? So angle between two lines, we know all we need is we need the direction vector. So for line 1, okay, we need the direction vector. Let's call it M1. For line 2, the direction vectors are M2. So very quickly, again, line 1, you notice that it's in Cartesian form, so it's not very helpful. So all you need to do is to create line 1 in vector form, right? So it's a vector equation. So quickly, we know that line 1 this is our line 1. Okay, we want to write in vector equation form. We can see that our R will just be equals to -8 lambda 2, right? We have 5 minus 2, okay, and his lambda will just be 1, and it will be -1 over here, right? So this will be the equation of the vector equation of line 1. Alright, and from here, right, we have, so from here, this is the so-called the direction vector of line 1. Right, so next up, what we can do is from the z-axis, right? The z-axis actually, if our line 2, right, is the z-axis, right, then actually just like the form of like beta 0. Right, it's any vector that lies along the z-axis will just be of the, maybe it can be represented by a scalar multiple of 0, 0, 1, right? And then so we just put it as a beta, where beta is a scalar, and so this will be the, you can see that this is the direction vector along the z-axis. So very quickly, when we want to find the angle between two lines, right, so cosine theta, let theta be the angle between the two lines, and what we're going to do is very quickly we just take the phi using the formula. It's just a M1 dot product with M2 over the magnitude. Okay, so 2, -2, 1, we just have a square root 9. Okay, and below we have a square root 1 as well. Okay, and with that, our answer gives us should be equals to 1/3. This means that cosine theta equals to 1/3, and theta should be equals to 70.5 degrees. Alright. Okay, so that is for part A. This is for question part A. Okay, sorry, part 1. Next up is for part 1. We need to find the position vector of the foot of perpendicular from the origin to line 1. Okay, position vector of the foot perpendicular from the origin to line 1. The foot perpendicular from the origin, so let's say the origin, we label it as a point. This is line 1, right? Then this end will be the foot of the perpendicular from the origin to line 1. So again, the idea that we use when we are dealing with finding the foot perpendicular from a point to a line is that we always try to create, first, number 1 is we try to express ON. Okay, try to express ON, okay, using L1. Okay, so here we try to express ON. After that, we use the fact that ON dot product with M1, where M1 is the direction vector, L1 equals to 0, right? And we can find a lambda, right? And then after that, using the lambda will give us a position vector of n. Okay, so that's the general idea. Alright, so next, what do we do? Okay, since you can see that since n lies on L1, so L1, as we have found earlier, L1 can be written in this form, right? It can be written in this form, which is -8, 5, 1 plus lambda 2, -2, 1 right? So this means that since n lies on lies on L, right? So ON can be written as negative 8 plus 2 lambda, 5 minus 2 lambda, and 1 plus lambda, right? For some lambda. Okay, and then from here, right, what do we do is that, okay, so we have this ON, right? And ON, okay, so ON, right, you see coincidentally because it comes from the origin, so this vector here is ON, right? So ON dot product with the direction vector of line 1, in this case this is the M1, right? The direction vector M1. Okay, and this direction vector over here, right, it dot product with M1 because they're perpendicular, right? Okay, it should give us 0. Okay, so that means, right, we take ON dot product with M, right, M1, it should give us 0. Oh, this implies that if I take negative 8 plus 2 lambda, 5 minus 2 lambda, and 1 plus lambda, right, if I dot product with M1, M1 is 2, negative 2, 1, it should give me 0. Okay, so if you don't understand, just pause the video for a while, think it through before you go on. Okay, so next up is just again dot product 1, 2, 3. So I have negative 16 plus 4 lambda, negative 10 plus 4 lambda plus 1 plus lambda equals to 0. Okay, simplifying this, you should get negative 26, negative 26, negative 25, 25, and then you have 4, 4, 8, 9, okay, right, and you should have very quickly, you should have negative 27 equals to 9 lambda, and finally lambda equals to 3. Okay, so at n, the point n, your lambda is equals to 3. Now since ON is written in the form of negative 8 plus 2 lambda, so negative 2 plus 3, 5 minus 2 lambda, 5 minus 2 of 3, and negative 1 plus lambda, so negative 1 plus 3. Okay, so negative 8 plus 6, you have negative 2, 5 minus 6, negative 1, negative 1 plus 3, you have 2, and this is the position vector of ON, where n is the flow of the perpendicular from the origin to line L. Okay, so this is for part 2. Right, next up we're going to find part 3. So part 3, right, okay, we need to find a point of intersection of line 1 and line 2. When find the point of intersection of line 1 and 2, very simple. What we do is we try to make x and y the subject on both sides, x, y, z the subject on both sides. So using line 1, right, from originally in line 1, okay, we know that in line 1, right, r, right, is equals to negative 8, 5, 1, right, plus lambda of 2, negative 2, 1, right, where lambda is a number. Okay, line 2, right, line 2 is actually the can be written in this form. So line 2 is let me see what's line 2 again. Oh, alpha 6, negative 4, 1. So line 2 is equals to alpha, then 6, negative 4, 1. Okay, 6, negative 4, 1. Okay, where alpha is also a real number. Okay, so from here, what we do is we try to solve them simultaneously. Okay, equating from the x components, right? Equating the x component from both line 1 and line 2, right? It means we are saying that negative 8 plus 2 lambda, suppose they intersect, right, is equals to 6 alpha. If we equate the y components, 5 minus 2 lambda will be equals to negative 4 alpha. If we equate the z components, 1 plus lambda will be equals to alpha. Right, so we can call this equation 1, equation 2, equation 3. Right, so it means that at the point of intersection, right, there exists there exists alpha and lambda such that, okay, at the point intersection these two are equal. Okay, so very quickly what you can do is you just solve them simultaneously. You can use your GC, you can use whatever. Okay, I hope you can do it, but I'm not going to show you. Right, so quickly from 1 and 2, maybe just take from 1 and 2, right, solve them simultaneously using algebra or using GC. The best is use GC, that is the fastest, right? So alpha should be negative 3 over 2. Alright, and lambda should be negative half. Alright, so from here, once we have that, then we have to check that equation 3 is true. Okay, so after that, make sure you start with equation 3. Make sure that equation 3, check equation 3. Okay, check equation 3 holds. After that, then you can sub into the either one equation. So if once I find alpha and then 3 over 2, then you can see that at the point intersection, r equals to negative 3 over 2, 6, negative 4, 1. So this should give you negative 9, positive 6, and negative 3 over 2. Alright, so this should be your point of intersection. Okay, this is the point of intersection between line 1 and line 2. Alright, this is for part 3. And next, okay, we want to find the vector equation of the reflection of the line L2 in the line L1. Okay, so this looks a bit challenging. So maybe what we need to do is we first try to deduce how this equation can work. Let's draw the line L1 first. Okay, let's draw the line L1 first. L1 looks like this, right? This one is my L1. Okay, so this is L1. Okay, then R is equals to negative 8, 5, negative 1 plus lambda of 2, negative 2, 1. Okay, this is my line 1. Okay, so now we know, right? Line 2, right? The point of intersection, suppose it from line 2 and line 1, right? Just now we have found that the point of intersection actually is what? Is actually given by negative 9, 6 and negative 3 over 2. So it's a negative 9, 6 and negative 3 over 2. Okay, so this was the point of intersection between we found in part 3, right? We know that L2, right? Okay, it actually the equation, right, looks like that. It's actually some like beta of, alpha of it's alpha of 6, negative 4 and 1. What does this mean? This means that actually, right, can you see that one thing that we may not realize, but one thing, can you see that here? Can you see that 0, 0 lies on this line? Lies on L2? Can, right? You can see that. That's a very nice result. So what does it mean? We go back to part 2. We go to part, remember just now part 2, what we're doing? We were finding, suppose that 0, 0 lies here, right? We were finding the, what are we finding? We're finding the foot of perpendicular from the origin all the way to, right, which is n, right? And n, which is done in part 2, was actually negative 2, 1, 2. Right? So this is the origin, and you can see it now with a drawing, the question looks so much clearer. So supposedly now we have this line, that this is the reflection of L2. We don't know what it looks like. Okay, so this is a reflection of L2 about L1. Okay, we can think about it, we just reflect. Okay, so maybe here, right? Maybe here, this portion, right, ON, let's say I call this M prime. Right, what will ON prime be? You can see actually ON prime is just like the 2 times of ON. Can you see? Right, ON prime just equals to 2 times of ON. And what will ON prime be? It's just basically, it's just 2 times of negative 2, 1, 2. And you see that I have negative 4, 2, 4. Okay, so this coordinate over here will be negative 4, 2, 4. So why am I doing this? Because you can see that now we are supposed to find the equation of this line, this yellow line. We need to find the vector equation of this line. Okay, but you can see that now, is it possible to do? Looks possible, right? Because now we actually have 2 points. With that, easily we can find 2 points. So suppose I call this n, right, and this is the n prime. Okay, then over here the position vector, the point intersection, maybe let's just call this maybe P, right? So very quickly for equation, let's find what's Pn. So Pn prime, right? This gives us the direction vector of the line of the answer. So Pn prime is just equals to -9, 6, -3/2, -9, 6, -2, -4, 2, 4, right? And, -4, 2, 4. Oh, sorry, I'm actually not finding Pn prime. I'm finding n prime p. Okay, n prime p. Oh, okay. So it's OP minus OP minus ON prime. Yeah. So from here, my answer should give -9. I should have -5. 6 minus -2. So this -2. So I should have 8. Just let me check. -2. -1. -2. Okay, apologies. This should be -1. So over here, this should be -2. Okay, common human error. So this is -2, -4, -2, 4. So I should have -5 and -11/2 as my n prime p. And n prime p actually gives me the direction vector, okay, of the line that's reflected. Okay, so -5, just recall it here. You can see that the direction vector here, right, is just equals to -5, 8, and -11/2. And we are almost done. We have one position vector, we can use either one. Okay, and we have one direction vector. So now we can easily find this equation. So this mirror line, right, vector equation of the line of L2 reflected about L1 is equals to R equals to, maybe just take any point, you just take the -9, 6, and 3/2 plus a scalar multiple, we just now I just call it gamma, -5, 8, and -11/2. Okay, where gamma is a real number. And so this question is really relatively quite hard. So what I suggest is if you see something like that and you don't know how to visualize it, the best is to draw it out. Okay, drawing out will help you.